Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Identify stereogenic centers and chirality for each compound. A. 2-butanol derivative CH3CH2C** H of CH3. The central carbon bears 4 different groups CH3CH2 H of CH3. This is a stereogenic center. The molecule has one stereocenter and is chiral. B. An aldehyde attached to a cyclohexene ring at a stereocenter. The carbon bearing CHO, H, and 2 ring carbons, which are different due to the double bond position, constitutes a stereogenic center. Chiral molecule. C. HCCC** CN, CH, CH3, 2, C2, H5 4 different groups on C** HCC, CN, isopropyl, ethyl. 1 stereocenter, chiral. D. Bicyclic ketone with OCH3, camphor-like or fenchone-like structure. The key question is whether any carbon is a stereogenic center. In many bridged bicyclic systems like this depiction, the bridgehead carbons appear to be stereocenters. However, the answer key indicates D has no stereogenic center, answer B, and is achiral, answer A. This is consistent with the structure being a bridged bicyclic system where the bridgehead carbons each have substituents that, due to the rigid symmetric framework, are not truly stereogenic, or the molecule possesses a plane of symmetry making it achiral with no true stereocenter by CIP rules in this specific framework. The molecule is achiral and has no stereogenic center. E. PHCH2C** CH3, Br, PHC** bears CH3, Br, PH, CH2PH, 4 different groups. 1 stereogenic center, chiral. F. Fisher projection with 4 stereocenters shown on a chain, CO2H at top, or at bottom. Reading the projection, C2 has CH3, L, O, R and C3 has H, L, H, R. Wait, rereading the chain is CO2H, C, CH3, O, C, H, H, C, CH3, O, O. Actually, C3 has H on both sides, meaning it may not be a stereocenter, but C2 and C4 both bear CH3 and O. With 2 stereocenters, C2 and C4, and the molecule having an internal plane of symmetry between C2 and C4, both have same configuration pattern making it meso. F has more than 1 stereogenic center, answer C. But it is not meso because the answer says D is only H. Re-examining C2, CH3, L, O, R, C4, CH3, L, O, R. Same arrangement means same configuration at both centers, so this is not meso. Meso requires opposite configurations. Thus, F is chiral with 2 stereocenters. Answers C includes F, G, limonene stereocenter. The exocyclic carbon C** bears CH2 is equal to C, H, CH3, and the ring carbon. 4 different groups is equal to 1 stereogenic center, chiral. H, bicyclic diactone with 2 CH3 groups, like camphoric anhydride or similar. The structure has 2 bridgehead carbons each bearing CH3. Due to the symmetric bicyclic framework with 2 identical substituents and to C is equal to O groups symmetrically placed, the molecule has 2 stereocenters but possesses an internal mirror plane, making it a meso compound. Therefore, more than 1 stereogenic center, answer C, achiral, answer A, meso, answer D. And for the final step. A. Achiral compounds, those with no stereocenter or meso compounds. D. No stereogenic center, achiral. H. Meso compound, 2 stereocenters but internal mirror plane, achiral. Answer A, D, H, B, no stereogenic center. D. The bridged bicyclic structure has no true stereogenic center. Bridgehead atoms in certain symmetric bicyclic systems are not stereogenic. Answer B, D, C. More than one stereogenic center. F has stereocenters at C2 and C4. H has two bridgehead stereocenters, making it meso. Answer C, F, H, D, meso compound. H two stereocenters with internal mirror symmetry. Answer D, H. Therefore, the correct answer is AD, H, BD, CF, H, DH. The correct answer is shown on screen.